Hey everybody, welcome to today's lesson. Today we're going to talk a little bit about what's called a polar and a non-polar covalent bond. And so we started talking yesterday all about covalent bonding. And remember, or just a reminder, that a covalent bond is going to be a bond in which electrons are shared and it's formed between two nonmetals. And today we're going to talk just a little bit about how we can further classify them as either what's called polar or nonpolar. So let's go ahead and dive right in. So the first thing I want to do is I want us to take a look at an example of a covalent molecule. Okay, so I'm going to go ahead and I'm just going to sketch out an example of a covalent molecule, hydrochloric acid, or HCl. And when we're doing this, or when we're drawing these structures, remember it's important to consider your two atoms and how many bonds they can maximum form, how many lone pairs they start with, and how many lone pairs they should end with, as well as just confirming that everybody's octet is satisfied. So hydrogen forms one bond, chlorine forms one bond. That makes it really nice and easy. They attach, they share. Hydrogen is one of our exceptions, so it requires only two valence electrons. Chlorine has the one bond and it had the three lone pairs to start and three lone pairs now to end, and therefore both are satisfied, both are fulfilling the octet rule. But my question is, how do I know that this is in fact considered a covalent molecule, or how do I know that this is a covalent bond? So again, just a refresher, the way that we're going to distinguish the fact that it's covalent is that hydrogen is a nonmetal, okay, and chlorine is a nonmetal. And what that means for us is that they both have high ionization energy and high electronegativity, okay, high ionization energy and high electronegativity. And that means that neither of these want to give away their electrons, okay? Aside from that, another way that we can confirm that this is considered covalent is by this line. Remember, this line represents a bond which is created from a sharing of electrons, and that's our shared pair of electrons, or our bonding pair of electrons. So HCl is considered covalent for, again, a variety of reasons. Two nonmetals, and they share electrons are the major reasons. Now, I want to focus just a moment on the question, on a new question, I guess, or just taking a look at that shared pair of electrons. And my question then becomes, how do I know if hydrogen and chlorine are sharing equally? So every year that I teach this in person, I always like to equate this to the idea of visiting my grandmother. My grandmother was such a fantastic woman, and when my sister and I used to go visit her, my grandmother would always give us lots of different treats or goodies. But I remember there were definitely a couple instances where my grandmother would either come to visit us or we'd go to visit her, and she would have only one candy bar for my sister and I. Now, I probably haven't told you this yet because we haven't really interacted in person, but I have an older sister. She's my best friend. Now, we didn't get along so much when we were younger, but she's 4 years older than me. And so with that candy bar, my grandmother would say, please share it. And we would run off. And my sister would always say, Kaylin, I'm so much older than you. I deserve more of this candy bar. I'm willing to give you a little bit of the candy bar, but I'm going to get more because I'm older, right? And of course, I just let it happen because what was the end result of that, right? She was bigger, she was stronger. I didn't want to mess around with it. I was fine. I took 1/3, she took 2/3. And so we still shared it, but we didn't share it equally. And so the question then becomes, how do I know if these are being shared equally? So do Cl and H share their electrons equally? Okay, and how are we going to figure that out? And so we have to kind of backtrack to the periodic table unit for just a moment and talk a little bit about one of our trends from the periodic table, which I'm sure you didn't think was going to come up in this unit, but actually it is most important in this unit, and that's electronegativity. So in the periodic table unit, I did not give you the full definition of electronegativity because I didn't think it was completely relevant at the moment, but I'm going to go ahead and just add a few words onto this definition. It's going to change how we see things and kind of hopefully point out how we're going to look at this bond and see if they're sharing those electrons equally. So electronegativity is going to be a measure of how well an atom attracts electrons in a chemical bond. And maybe using the word how well it attracts isn't the right way of saying that, but it's going to be essentially how strong, what is the relative strength of that attraction, okay? So we want to investigate the electronegativity values of both hydrogen and chlorine to tell us, is there an equal advantage of sharing those electrons, or are they not being shared equally? And if that's the case, who is holding on to those electrons more? So let's go ahead and let's take a look at the HCl bond a little bit closer. So I'm going to go ahead and I'm just going to sketch out this HCl bond, again, HCl. And what I want us to do is I want us to take a moment and I want us to look up those electronegativity values. Now, if you want to practice this on your own, feel free to pause the video and take a moment and use your reference table S to look up those electronegativity values, okay? Or if you are confident in your ability to do so, you can just hang with me here. So looking them up in my reference table, I noticed that my hydrogen has an electronegativity of 2.2. and my chlorine has an electronegativity of 3.4, okay? And so what does this information tell us? This information tells us that chlorine has the higher electronegativity, and therefore it has a stronger hold or a stronger attraction to the electrons in the bond. So what does that mean then? Do you think these electrons are being shared equally? And the answer is no, okay? The electrons are not being shared equally. So this right here, this bond between HCl is an example of what we call a polar covalent bond. Now, where does that term polar come from? Well, think about where you've heard poles before, okay? So we've heard of poles like North and South Pole, or the poles of a magnet, so positive and negative. And so that idea of pole is creating two separate sides and a bond that has an unequal sharing of electrons, okay? So this is going to be a bond in which electrons are not shared equally. And we'll talk about the implications of that in just a moment. I do, however, want to show you an example of a bond in which electrons are shared equally. So let's consider a molecule like H2, okay? So H bonded to another H, again, another example of a diatomic, H2 hydrogen, and this right off the bat should be kind of obvious to you that it's going to be shared equally just because they're identical atoms. So I would liken this to, or the HCl bond I would liken to maybe me and my older sister sharing a candy bar, but H versus H might be more like identical twins sharing a candy bar. So our electronegativity value is 2.2, and our electronegativity value is 2.2, and because they have equal electronegativity values, there is an equal sharing of electrons, and they share them perfectly equal. Okay? And we call this type of bond a nonpolar covalent bond. I'm sorry. Okay, so this is a nonpolar, let's color code that, nonpolar covalent bond. Okay, and so this is going to be a bond in which electrons, let's move my picture out of the way, okay, are shared equally. All right. So we have these two different types of bonds, and they really just measure whether or not electrons are shared equally just by comparing those electronegativity values. Now, nonpolar bonds shared equally, beautiful, nothing happens with that. But I do want to take a moment to just talk a little bit about what that polar covalent bond and what the result of that is. So I'm going to just go ahead and give you a new example, and I'm going to make it a really drastic example of H and F. Okay, because as you may remember from your from the periodic table unit, fluorine is our most electronegative element. And so if we are taking a look at H and F here for polar covalent bond, again, H has a 2.2, F has a 4.0. So F has a stronger hold on those electrons. Where else have we seen a non-equal share, or not even a non-equal share, but where else have we seen the situation where somebody else has a stronger hold on electrons? So think about it in terms of ionic bonding. Sodium gives away its electron to, let's say, fluorine, since this is the case of HF. So sodium, if it was sodium, it would give away its electron completely. When we do that, what happens? We create a positive ion and a negative ion. Well, in this instance with HF, we're not donating our electron completely, but we are not sharing it equally, and fluorine is holding more of that negative charge. So unlike ionic compounds, right, we're not creating a full positive and a full negative charge, but we can't quite say that there's not this imbalance of charge created because they're not sharing equally. So we create what is called a dipole, or an unequal sharing, so that there is a creation of a partial positive and a partial negative charge. Now, every year that I do this, students really freak out about it and think it's really hard, but let's just kind of try to think about this logically. Who's going to be assigned the partial negative charge? Well, in the instance of sodium and fluorine and the ionic compound that's created, sodium gives away its electron to fluorine, and fluorine forms a -1, right, because it gained that electron. So if fluorine is holding on to those electrons that are being shared a little bit more than hydrogen, then fluorine is going to be a little bit more negative than hydrogen, and hydrogen is going to be a little bit more positive. And that's the creation of our dipole. How do I represent this dipole? We typically use partial positive and partial negative charges to show this. So again, do not freak out about the sign of partial positive and partial negative. Just bear with me here, and we'll do lots of practice drawing these. So for partial positive and partial negative, the partial symbol is represented. I'm going to do it right up on the screen below where the camera recording is right now. But a partial is almost like this incomplete figure 8. This represents a partial charge. And so our partial negative lies to the side where fluorine is, right? Again, fluorine is holding on to those electrons, which carry a negative charge a little bit more than the hydrogen. Hydrogen, therefore, carries a partial positive charge. This isn't, we don't always have to label these, but it is going to become really important for us for our next lesson to really understand how to assign those partial positive and partial negative charges. So I do want to go ahead and make note right below this that the partial negative is going to always go to the more electronegative element, and the partial positive is always going to go to the less electronegative element. And so if you're feeling really overwhelmed, that's another way to just think of it. Your partial negative is always going to go to the more electronegative, partial positive to the less electronegative. We're almost done, but I do want to touch base really quickly on just the idea of ionic versus covalent again. So just thinking about this, concept of covalent bonds now, in the sense that whether or not they're sharing equally, we use electronegativity to measure that. So why, or in terms of electronegativity, why do you think it becomes an ionic bond? Well, in order to give us an example, again, let's use sodium and fluorine. So ionic bonds have such a large electronegativity difference, there is no sharing. Okay, so there is no sharing. So if we think of something like Na, which has a 0.9 electronegativity, and F, which has an electronegativity of 4.0, notice that my electronegativity difference here is 3.1. Okay, and that's huge. And therefore, sodium, instead of sharing, just gives away its electron. Okay, so this leads me to my last point, which is we have this term called ionic character. And ionic character can be used in reference to covalent bonds. And the ionic character is a measure of how ionic a substance is. It sounds ridiculous, but let me just clarify. So ionic character is going to be the measure of how ionic something is. Okay, so how ionic something is. And by something I mean a bond. But what I mean to say is that the greater the difference in electronegativity equals more ionic. So I could give you a list of covalent bonds like HH, OH, NH and ask you which of these behaves most ionically. Even though they're all covalent bonds, we could look at their electronegativity differences and ask ourselves which one behaves most like an ionic bond. All right, everybody, that's it for today. Thank you so much. Have a great rest of your day, and I will see you tomorrow.